In this video, we will complete lesson 1.1 and lesson 1.2 of Computer Science 0478 Cambridge IGCSE Chapter 1 Data Representation. Okay, so I want to start off by defining what is 2's complement, okay, which is the last part of lesson 1.1. Okay, 2's complement is a binary conversion method which allows the possibility of representing negative integers. So far in the first lesson that we have learned about the conversion methods, we have only been learning how to convert these methods, or how to convert a binary to a hexadecimal or a hexadecimal to denary and vice versa, okay, using positive integers. Now we're gonna have a look at how to convert these by using negative integers, okay? So in a 2's complement, the leftmost bit is changed to a negative value regardless of the operation, okay? For example, for an 8-bit number, the value 128 is changed to negative 28 because it's the most left bit number on an 8-bit number, but all the other headings remain the same. We'll have a look at some examples, so don't worry about that. Writing positive binary number in 2's complement. So to write a positive number in binary using 2's complement, just make the last bit heading value negative and continue to solve normally. So for example, this is your denary number and I want to convert it to a binary number. What am I going to do? I'm going to first make a table. You're going to first start off by making a table of the headings. Now you're going to put a 1 under all the numbers that add up to give you 19, correct? So up till 16 is okay, but if you choose to go all the way up to negative 128, then the left last digit is going to become negative, okay? So keep everything the same, solve it as it is, but just make the last one negative. Alright, let's have a look at another example. How to convert a positive denary to a binary using 2's complement. Again, change the last left heading to the negative value. So converting 39 into an 8-bit binary by 2's complement, we're going to use the same method. Use a table, put the binary headings, put the numbers under that add up to give you, put 1 under the numbers that add up to give you 39, and make the last left heading negative, okay? Now if you're looking to convert a negative denary into binary, okay, it's going to be slightly different, okay? You're going to start off by converting the given denary to binary normally, as if it were positive. So just perform the operations normally, okay? After you solve it normally, now this is where the plot twist comes in. You make the last digit heading negative value, and then from the right to the left, invert every bit after the first one, okay? So let's have a look, okay? Negative 23 in binary in 6 bits. Okay, so how you convert the denary to binary? Normally, imagine as if it's positive. Put the headings, put 1 under each one that adds up to give you 23. Now what are you going to do? You're going to put a negative in the left last digit, and you're going to invert from right to left after the first one. So 1 remains the same. After the first one, 1 will become 0, 1 will become 0, 0 will become 1, 1 will become 0, 0 will become 1. Okay, so steps are simple. Solve as if it was normal, make the left last heading negative, invert after the first one from right to left. Okay, this is a quick example, you can solve it by yourself. Converting binary to negative denary using 2's complement. Again, convert the given number to binary to denary as if it was positive, make the last left heading negative, invert after the first one. You can also pause the video here and solve your examples. Basically, after that, we have concluded lesson 1.1. Now we will be starting lesson 1.2 in chapter 1. So we're going to start off by defining what is the ASCII code and the Unicode, okay? So before we come here, let's understand what is a character code, okay? A character code is a binary number generated that represents a specific symbol for a specific key on the keyboard. Basically, when you press a button on the keyboard, what happens is that a binary number is generated, because of course, you know, the computer can only understand binary format. So when you press a letter on the keyboard, a binary number is generated for the letter that you pressed, and for each letter that you press, there is a binary number that is generated, okay? And so in that case, that character code is that binary number that is generated for a specific key on the keyboard. Again, a binary number generated for a specific key on the keyboard. Okay, it is a complete collection of character codes, and it makes a character set. So if you have let's say you press K on the keyboard, it might generate a random pattern like 011 011 01. Okay, But let's say you press KARL. That's a character set, because patterns of binary digits are going to be generated for the big amount of number of letters and character keys that you have inputted into from the keyboard. Okay, so character code is one binary number for a single letter or something. Character set is a pattern of binary numbers for many letters. Okay, now that we know that, we can understand the ASCII code and the Unicode system. The ASCII code stands for American Standard Code of Information and Interchange. The standard ASCII code character set consists of 7-bit codes, 0 to 127 in binary or 00 to 7F in hexadecimal, which represent letters, numbers, and characters found on a standard keyboard. Now, the disadvantage of the ASCII is that it does not represent the characters that are in the non-Western languages, for example Chinese and etc. So that is a really big disadvantage, okay? Though yeah, we do have the extended ASCII code, which is like, you know, an 8-bit character set. It represents 256 different languages and is also useful for European languages as well as Greek and Roman letters. But again, the cons are still the cons, and we had to come up, or let's not say we, but something had to be better. There has to be some advancement done, right? That advancement was the Unicode. The Unicode turned out to be a code system that uses either 8, 16, or 32 bits per character to represent all languages in the world, supporting many operating systems, search engines, and internet browsers used globally. Okay? Here are some key points to consider about the Unicode. The Unicode system, okay, so the ASCII use 16 bits, whereas the Unicode can use 4 bytes per character. Since the Unicode is larger than ASCII, it takes, of course, more storage, and 32 bits of the Unicode allows up to 147, 43, 647 various characters. Okay, let's move on and understand what are the 5 goals of the Unicode. Okay, so the Unicode was created to produce a more efficient coding system than the ASCII code, to create a universal standard that commanded all languages and writing systems, to adapt uniform coding. Each character is encoded as a 16 or 32-bit code, and let each 16-bit or 32-bit value represent the same character. And lastly, it was also to reserve part of the code for private use, to enable a user to assign codes for their own characters and symbols. Now that we have finished from character codes, character sets, Unicode, and ASCII code, let's come to sound and image size. So, how do we represent sounds? We know that sound waves are vibrations. Actually, if you refer to my physics videos, you will know that sound waves are longitudinal waves. Okay? So they are vibrations in the air that the human ear senses and interprets them as sound. So each sound wave has a frequency, wavelength, and amplitude. Amplitude specifies the loudness of the sound. Now, sound to computer. How does the computer actually understand the sound? Well, that is because sound is an analog, okay? But computers cannot work with analog data. They only work with binary data. So what happens? Well, something called sampling happens. Sound is sampled to be stored in a computer. Sampling meaning a measure of the amplitude of sound wave using an ADC at regular time intervals. ADC is your analog to digital converter. It converts analog data from your mouth into digital format, zeros and ones, binary format to be understood by the computer. How is this process occurred? It occurs during sampling, where sound is converted at regular time intervals. As you can see, at regular time intervals, the sound is converted using an ADC. Okay? Again, X row shows the time intervals, Y axis shows the amplitude of the sound. Now, increasing the number of possible values used to represent the sound amplitude will also increase the accuracy of the sound sampled. Now, ADC will convert the analog to the digital, and for the digital to come out for us to be heard, it's converted from a digital to an analog converter. Here are some quick definitions. Sampling resolution is basically the bit depth or number of bits per sample. Sampling rate is the number of sound sample taken per second. It is measured in hertz because 1 hertz is 1 sample per second. How is the sample rate recorded as sound? Well, basically the amplitude of the sound wave is determined at regular time intervals. After you get an approximate of the sound wave, each sample is then measured as a series of binary digits. Now, what are some benefits and disadvantages of having a large sampling resolution? Benefits include a larger dynamic range, of course, better sound quality, less sound distortion. Drawbacks include large file size, takes longer to download, requires more processing power, more storage, and etc. Okay, that's up for sound. Let's come to image. So a bitmap image is an image made of two-dimensional series of pixels. A pixel are picture elements. They're like small dots of colors arranged in a grid. Pixels can take many different shapes. They form pixels in an image. Basically, the more pixels there are in an image, the closer you can get to the original image and the more clear it is. Each pixel is represented by a binary digit or value that is stored in the computer as binary numbers. For example, a black and white image will only require 1 bit per pixel, so each pixel can be two colors, either 1 or 0, where 1 can represent white and 0 can represent black, or vice versa. Metadata is additional data stored on an image to provide information such as dimensions of an image, image resolution, date and time the image was taken, and etc., like common, basic, and usual data. Now, image resolution is the number of pixels inside an image that make up the image. So, of course, we learned that pixels are picture elements. Now, the number of pixels present inside an image that make up this image is known as the image resolution. You're usually going to see this as 2 digits with a multiplication sign in between, allowing you to understand what is the horizontal and what is the vertical resolution. So, to find the total resolution, you must multiply the horizontal by the vertical. As for color depth is the number of bits used to represent each color in an image. Okay, example, an 8-bit color depth represents 256 colors. A modern computer have 24 bits of color depth. Okay, now here are some image facts. The size and quality is directly proportional to the image resolution, of course, and color depth. If you increase the size and if you increase the color depth, okay, you are increasing the quality and you are increasing the resolution of the image. Of course, drawbacks of high resolution, it can limit storage space and it will impact the downloading speed and transfer over the internet. Bit is the smallest basic unit made up of all computer systems. Byte is a group of 8 bits, 1 byte equals 8 bit, and nibble is a half a byte, so basically 4 bits. Now let's have a look at some examples on how to calculate file size. So the formula of file size is image resolution is equal to in pixels, color times color depth in bits. So steps to solve: multiply the number of pixels by the color depth, add all together to get the image of the size. Now divide by 8 to get it in bytes, and if it's necessary, multiply by any or divide by any other value to achieve a different unit. For example, a photo was taken at this much pixels and uses a color depth at 32 bits. How many photos of this size would fit into a memory stick of 64 GB? So we're going to find first the image resolution, multiplying we're going to find the file size, multiplying the image resolution by the color depth, then multiplying by 32 because we have 32 bits, which is equal to this, divided by, now we're going to divide this by 8 to get it in bytes, and then we're going to find the answer of this from bytes using the 2/3 of the space. So the number of photos would be the storage size in bytes divided by the image size. Find both and you're going to find the number of photos. Okay, let's solve this example. Actually, let's first understand how to calculate sound. Sound is basically very simple. The size of the sound file is the sample rate in hertz times the sample resolution times the length of the sample in seconds. So you multiply it all together. If any repeated change, of course, multiply it again, divide by 8 to get in bytes, and then again divide the sound in bytes to convert the megabytes as a final answer into a megabyte value. Okay. So for example, an audio CD has a sample rate of 44/100 and a sample resolution of 16 bits. The music being sampled uses 2 channels. Calculate the size for a 16-minute recording. So we're going to multiply the sample resolution, length of the sample, and sample rate. First, getting this answer, we're going to now multiply by 2 because there are 2 channels. Then we'll divide. I want you to divide your answer by 8 to get your answer in bytes. Okay? Again, I will review the steps. We use the formula, sample rate, sample resolution, length of the sample. Then multiply it, get the answer. Multiply it by the number of channels, get the answer. Divide that by the number 8 bytes to get your answer in bytes. From here then, you can multiply or divide by any other value to convert it to any desired unit. Okay? Just remember, from bit to byte, it is divide by 8, byte to bit, multiply by 8. If you're converting from a small to larger unit, you divide. If you're converting from a bigger to smaller unit, you multiply. As for the last part of this topic, we will be considering the data compression part. So data compression stands for reducing the size of a large image or sound file. Why do we use data compression? Why do we want to reduce the size? Okay, well, there are many reasons to consider here. First one, we want to save storage on the space of devices and disk space. If you compress the file, it's going to take up less storage, correct? Another thing, we want to reduce the time taken to stream or send files over the internet. Less space, less storage, faster transmission. We want to reduce traffic over the internet. Okay, we want to reduce the file size for lower cost of transmission over the internet and less bandwidth. Bandwidth is the minimum rate of transfer of data across a network, which is measured in bits per second whenever a file is downloaded. Now, there are common compression file types. We have your JPEG and GPEG, which is lossy compressed, your GIF, lossy compressed, MP3, MP4, lossy compressed, PNG, lossless compressed, and PDF, none. What do we mean by lossy and lossless? We'll have a look at it right now. So, lossy file compression is a file compression algorithm that eliminates unnecessary data from the file. Okay, so the original file from lossy compression cannot be restored at any case. Lossy file compression results in some loss of data compared to the original file, and lossy algorithm decides itself which parts of the file it needs to remove. Lossy files are small, okay, and they are good for considering high rates of data transfer. Now, we can use these lossy algorithms in usually images to reduce the resolution, or in sound files to reduce the sampling rate. For examples of some of these is the MPEG-3 or MP3 files used for playing music videos, okay? They remove the sound, they basically remove sound from the video that is outside the human ear range, okay? So basically, if two sounds are played at the same time, the less one that cannot be heard will be eliminated. Another example is the GPEG. It is a lossy file compression algorithm that will be used for a bitmap image, basing on the two concepts of reducing the file size by removing pixels of which are altered by or not altered by the brightness, and our human eyes cannot detect it. As for your lossless file compression, it is a file compression algorithm designed so none of the original file data is lost. You can restore your original file data. Okay, for example, the RLE, run length encoding. Basically, it reduces strips of data, okay, strings of data. Any repeated colors or any repeated data in the system, it basically removes that. But again, your initial data can be restored in the lossless, okay? Skipping this page, going to the last page. This is just a comparison between lossy and lossless. I advise you to pause the video here and have a look at this comparison between the lossy and lossless type of data compression. And that was it for this sheet. Other than that, if you have any questions, feel free to ask me in the comments below, and I'll see you in the next one.